Now we're going to have fun and launch a pinball. See what happens. So we've compressed a spring by 5 centimeters, and we know the spring constant is 120 newton meters. We know the incline of the pinball table is 10 degrees. And we want to know how far, that does not look like an it, how far does it go? And we also want to know the velocity at release. So let's make a list of some of the things we know. We know that K is 120 newton meters. We know that delta X is, let's see, 5 centimeters times 10 to the negative 2, so 0.05 meters. And we know that the incline is 10 degrees. So let's think about what's going to happen here. So I've made some notes, and one of the notes that I'm going to make is I'm going to call where it's at when it's compressed against the spring. I'm going to label that as the height equals 0. So my comparison height is going to be after it's traveled 5 centimeters. That's going to be the one that I'm interested in. So at the beginning, when it's at rest and compressed against the spring, let's see what I have. I have spring potential energy. What is that spring potential energy going to go into? Well, it's adding in kinetic energy, so it's making the ball move. So it's got kinetic energy as it's moving, and it's going to travel that 5 centimeters. That means it's also gaining height. Actually, let me be consistent. So potential energy from height. So we can write this as, let's see, I have 1/2 kx squared equals 1/2 mv squared plus mgh. Let's see, what the thing I want is the velocity, so let's just go ahead and move some things around before we figure out how we're going to solve all this. So 1/2 kx squared minus mgh equals 1/2 mv squared. Or, let's see, we're going to divide by m and multiply by 2. So I'll get kx squared minus 2 mgh. That just comes from this fraction. I've inverted it and multiplied it over here. So 2 mgh, and now I'm going to divide by the m, divided by mass, equals v squared. Seems pretty straightforward. The only problem is, the only thing we don't have is what this height actually is. So let's just simplify that and remember that that 10-degree incline is still just 10 degrees. I've just moved where I've defined as 0. So I have 10 degrees here, and let's see, I want h, and I know that this is 0.05. So let's see, sine opposite over hypotenuse, so 0.05 times sine of 10 degrees will equal my h. Now I can actually solve for this. So I'll get kx squared minus 2mg 0.05 times sine of 10 divided by mass. Take the square root of that whole mess, and that gives me my velocity. And then it wants to know how high I'm going to go. Well, I'm just going to reverse engineer what I just did. So from this point then, the spring is no longer acting after I've gotten this initial velocity. So I'll have 1/2 mv squared, so my kinetic energy is all going to go into moving it up the hill, mgh. So my masses will cancel, and I'll end up with, let's see, v squared over 2g equals h. Well, it wants to know how far up the ramp I went. So that's going to be this distance here, this actual displacement. So to find that, what do I need to do? Well, let's see. I know that h equals, this is my displacement. So this would be like my delta x, if you will, or delta y, or whatever you want to call it. So my delta x sine of 10 equals h. So I can go ahead and make that substitution in here. Then I have v squared over 2g equals x sine 10. And that's it. So for this final thing then, my distance that I travel up the hill is going to be v squared divided by 2g sine 10. So once I pull that all together, I get that the velocity after it leaves the spring is 1.682 meters per second. And I did kind of leave off a little important thing there, that the mass of this thing is 0.1 kilograms. Start solving it and it's like, oh, we don't have mass. Yes, we do. All right, so there's its velocity, and then the distance up the hill, putting all the numbers in, is the 0.83 meters. So it's going to go 0.83 meters up the ramp, and that's it. So in terms of considering these things, like a fun thing to do that I would challenge you to try is change the ball into a block and put friction on the darn hill. Then solve it and see how fast it's going after it's launched, and see how far up it goes. See if you can tackle that challenge, and maybe I'll post a video coming up with an answer there.